Okay, so this is the Precalculus 2, section 4.8 notes on applications of trig functions. So the main concept in the beginning of this section is that of what's called solving a right triangle. So in prior sections, you've been given a couple pieces of a triangle and you needed to find one other missing piece. Basically, the concept of solving a right triangle means that you are once again given a few pieces, but you want to now find all the remaining sides and angles. So that's basically what we're going to do. You'll find that this is all very much a review of things we've done before, but we're kind of all bringing it together. So if you look at the triangle at the top here, just recall that if you have an angle A, let's say, then you always label the side opposite it with the lowercase version of that. So that allows us to label things quite easily when looking at the triangles. For example, if we look at number 1 here, it says the angle A is 27 degrees, and it says side B is 12. Well, if angle B is here, then side B has to be opposite it. So you'll see that we have two missing pieces, including, of course, the right angle. So we should be able to find what the missing pieces are going to be. So what we want to do is we want to label the other side. So for example, let's say we have little a. So that's opposite angle A. So how do we find that missing side? Well, we want to look at this angle 27 and we want to look at what pieces are actually provided. So here we have the side opposite and we have the side adjacent. So that clearly is going to be the tangent function. So we want to take the tangent of 27 degrees, and that is equal to a over 12. From previous lessons, you learned that to solve that, we just have to multiply both sides by 12 and get a is equal to 12 times the tangent of 27. Remember, before you put this in the calculator, make sure that your mode is in degrees rather than radians, in case that was changed. So if we do this in the calculator, we should get 6.11 approximately as that missing side. Okay, so we can move on and continue to do that throughout the picture. For example, what about little c? Well, with little c, we should again be able to use the two missing pieces or the two given pieces in order to find that side. So if you ignore a for a second over on the right side, you can look at c and 12 with our angle 27. So you can look at that and say, well, that's the adjacent and that is the hypotenuse. So we go, all right, well, what's adjacent over hypotenuse? That's cosine. So the cosine of 27 degrees is going to be equal to 12 over c. Okay, so you can, once again, in 2 steps algebraically, you can solve this for c, but remember I gave you a little bit of a shortcut. If you'd like, you can put this over 1, and then you do not change the truth of the proportion if you swap diagonal values. So essentially, you're going to get c is equal to 12 over the cosine of 27 degrees. Once again, you do this in the calculator, you're going to get 13.47. Okay, so we have both our missing sides. If you look at the picture, basically you can sort of summarize. You can say, all right, so we got 6.11 over here. We got 13.47 over here. So the only thing that's missing is this angle B, but angle B should be pretty straightforward. So angle B is basically just going to be, you have your full 180 degrees in a triangle, and you want to subtract the sum of the two angles that are there, and that's going to give us 63 degrees for angle B. Okay, so these are the missing parts. Now, hopefully you notice from my strategy here, I purposely tried to use pieces that I didn't round already. So yes, I could have used 16.11 or 6.11 in order to find another side or angle, but I tried not to do that just because I had rounded to find that value and already created error. So can you always do that? Not necessarily, but I tried to do it as best I could in this scenario for this problem. So if we move on to number 2, you'll see that it's a very similar situation that we're going to work with. So We have letter A in this scenario, which is opposite angle A, is 10. Letter B, which is opposite angle B, is 20. Okay, so we can easily find the missing side C using a very straightforward Pythagorean theorem, which is c squared is equal to 10 squared plus 20 squared. This will be c squared is equal to 100 plus 400, which is 500. And c is equal to the positive and negative square root of 500. So just remember that we're looking for perfect squares here if you want to simplify this guy. So root 500 is the same as root 100 times root 5. And of course, root 100 is 10. So this is going to be plus or minus 10 root 5, which we can then put in our picture over here. 10 root 5. And this is obviously an exact value, which is always nice to have. So now we have a setup here where we can find the missing angles. But remember, when we're let's say if we want to find angle A, this is a little bit different of a setup. So in order to find a missing angle, we have to return to the concept of an inverse trig function. So we would say, let's say we want to find the angle A. We would need to do the tangent of A is equal to opposite over adjacent 10 over 20. So 10 over 20 from this angle, which we don't know, will give us that value. So remember, if we want to find the actual angle A, there's no algebraic way to do that. We just have to do the tangent inverse of 10 over 20 into our calculators, and we get a rounded to 2 decimal place value of 26.57 degrees. Okay, so finding angle B, once we have this value, we have one of two options. We can either use trig if we want, or we can subtract from 90. That's completely up to you. Most students would be like, would probably tend towards using, well, let's do 180 minus the sum of 90 and 26.57. This is going to give us 63.43 degrees. You can always check that using trigonometry. You could do the tangent inverse of 20 over 10, which is the opposite of the other one, and that would give you that same amount. So therefore, you do have now all of the pieces that we were looking for in this problem. So these problems are pretty straightforward. I think many of you will coast through them based on earlier material, but you'll see that if I ask for you to solve a right triangle, you need to find all of the remaining missing pieces using your calculator. Okay, so let's talk about some word problems involving trigonometry. It says a hot air balloon is rising vertically from a point on level ground 125 feet from the point directly under the passenger compartment. The angle of elevation to the balloon changes from 19.2 degrees to 31.7 degrees. How far does the balloon rise during that period? Okay, so the picture does look a little complicated, but generally what they're getting at here is we're at a point on the ground somewhere over here that is 125 feet away from directly under the balloon vertically. So essentially what happened is in the beginning, we have this amount of height that the balloon has gotten to when the angle of elevation was 19.2 degrees. But then we have another height that the balloon has gotten to after the angle of elevation was 31.7 degrees. Now just remember that the angle of elevation is when you go from your horizon line and you go up from there. So in this case, our horizon is essentially the ground of this problem. So right here, the ground goes across the horizon, and then we go up here and then up from there, both from the horizon line to get those measures. So what's interesting about this is we can put some variables on these. And in reality, if we want to find the missing information here, which is going to be how far the balloon has risen since the change of angle of elevation, then all we would have to do is take our y and subtract our x after we calculate them. It's a pretty simple, straightforward computation, but we need trig in order to do this. So one of the things we want to take note of is I'm just going to redraw the lower triangle down there, which is 125 feet on this side, 19.2 degrees over here, and x. So if we look at that, we can clearly see we have a right triangle where we have an angle of 19.2 degrees. We have opposite and we have adjacent. So we should be able to use our tangent function of that specific angle, 19.2 degrees, and that should be equal to x over 125. Okay, so algebraically we multiply both sides by 125 and we'll get x is equal to 125 times the tangent of 19.2 degrees. Again, remember, make sure your calculator is in degrees. You can perform this calculation and get 43.53 feet. Okay, so this is how far the balloon rose originally from the ground, right? So now we have to figure out how far it rose from the ground up to the balloon. So how do we do that? Well, we also have a bigger triangle, okay, where we have a 31.7 degree angle, and we still have 125 feet down here, but this time we labeled this y. So you'll see that it's exactly the same setup, so therefore tangent will be used again. 31.7 degrees is equal to y over 125. We use, again, multiply both sides by 125 and get y is equal to 125 times the tangent of 31.7, which will give us approximately 77.20 feet. Okay, and as we spoke of before, how do we find the missing piece right here? How far has it risen since the change in angle of elevation? We just need to take our value of y and subtract x. So y minus x is going to be 77.20 minus 43.53, which is going to give us approximately 33.67 feet. Please remember your labels on exams. That is a pretty big deal on any of these problems, but that'll be our result. Now, one small thing about this, I find that students that really make a mistake here is what they'll do is they'll concentrate their vision on just this triangle right here. Okay, well, what's the problem with that? That is not a right triangle. So right now, we do not have any methods for dealing with triangles with trigonometry-related things that are not right. In this case, we can't do anything with that one triangle. Even though we know the missing side is a part of that triangle, we can't directly find that side, which means we have to indirectly find it by using the two right triangles. Number 4, a circus high wire act walks up an approach wire to reach a high wire. The approach wire is 122 feet long and is currently anchored, so it forms a maximum allowable angle of 35 degrees with the ground. Okay, so look in our picture. Basically, we have a person who's walking up this wire to reach the high wire. Okay, so you'll see that the angle down here is at 35 degrees. So they're saying that this is 122 feet long at the beginning of our problem. Continuing, the aerialists have found the approach wire to be a bit steep, so they have moved 30 feet backwards. So look what they're doing. They're moving 30 feet backwards and anchor the wire there instead. Find the new angle the approach wire makes with the ground. Okay, so our old angle was 35 degrees. So now our new angle is going to be over here, which we will call theta. So therefore, we basically have all the information set up from the problem that we need to do the problem. So this is a little bit more complicated. Again, just like the previous problem that I pointed out at the end, that angle theta is in a very thin, non-right triangle on the left side with a side of 30 feet. But because it's not a right triangle, we have to stick to finding a right triangle where this angle theta is in. And what triangle is that? The very big triangle. ADC. So if you look at that triangle, essentially what we would need is to find AD and CD in order to find the missing angle theta, and we could use that using tangent because that's opposite over adjacent. But we first need to find those sides, before we can do so. Now, if you look at the smaller triangle, which is BDC, we're actually given an angle and a side, and we of course know that this is a right angle. So we should be able to use basic trig in order to find those missing pieces. We'll call this x and we'll call this y. So let's start with x. Well, if we have 35 as our angle right here, if we look over to x and then 122, that looks like opposite hypotenuse. So that is sine. So we can do the sine of 35 is equal to x over 122. Multiplying both sides by 122, we get 122 times the sine of 35, which is going to give us 69.98 feet for our height from the ground to the high wire. If looking at this standpoint, if you're looking at y, actually what we're going to do is this. We're going to make this a little bit easier here. So let's stick to making just this y for now. So if we look at those pieces, if we do 35y and 122, then we can look at that and say, oh, well, that's adjacent hypotenuse, which is cosine. So if we do the cosine of 35 is equal to y over 122, we'll have y is equal to 122 times the cosine of 35, which is going to be approximately 99.94. Okay, so you might ask, why did I change it from the whole side to just BD? Well, we need to find the missing piece using the smaller triangle, and y is a part of the smaller triangle. Now, what can we do now? Well, luckily, because we know that this is 99.94, and we know that this is 69.98, we also now know the big side, because this is going to be 30 plus 99.94, which is going to give us approximately 129.94. So if we look right now at the very big triangle, which is ADC, we have a right triangle with a side of 69.98 over here and a side of 129.94 and theta. So if we have these measurements, you can clearly see that we have an opposite over adjacent situation. So the tangent of theta should be 69.98 divided by 129.94. Remember, the only way to find an angle in these scenarios is to use the inverse version of the trig function. So we will get this, which is going to give us approximately 28.30 degrees. Okay, this is the new angle of that wire, and of course, it's got to be smaller based on the way the picture works. If you go out farther, you create a smaller angle, and therefore a less steep wire, which is the new wire going across here. Now, just take a note when doing these problems, be careful with rounding. You'll see that I did round to 2 decimal places, which means this is filled with some error. We wouldn't want to do this if we were doing a technical, like, building situation. But for these purposes and these informal problems, 2 decimal places is okay. The last application in this section is called bearings. Bearings are used in nautical travel on the sea, so we use this as an interesting application of trig. First thing you have to learn is how measurements and directions are actually displayed in bearing language. So we're going to start there. So it says right here, it says general, each bearing has 3 parts. So if we look at an example of a bearing measurement, you'll see that it starts with N. So logically, that is north. So it is always going to start with a north or a south. If we look over here at a typical, northeast, southwest kind of setup, it almost looks like a graph. If you look above the west-east line, basically what you have is north and below is south. So if the direction is, above this line somehow, right, then that means we're going to have north as the measurement. If it's below that line, east-west line, we're going to have south as the measurement. So what else is important? So this is going to be sort of the key thing. It says the measure of the acute angle as measured from the north-south line. So of course the north-south line is this one, right? North-south line. So that is the line that we are going to be measuring the angle from. So if you look closely at this, you'll see that this was measured as 40 degrees. So you can see that when we draw this line here, we're measuring the angle from the north-south line. So this is a key part of bearing measurements, is realizing it's actually the opposite of a reference angle. So a reference angle is always to the x-axis, which would be here. So just realize that that's going to be a big part of the measurement. And then lastly, the east or west side will also be included, whether it's on the east side or west side of the north-south line. So this is in the northeast quadrant over here. So you'll see that N and E are the variables that are in the beginning and the end, and 40 degrees is measured from the north-south line. So let's go down to the example here, this example, and take a peek at number 5. Take a peek at these measurements. So for example, if I want to know the bearing from O to A, so we're talking about this bearing right here, O to A, we would look at that and say, okay, clearly in the northeast quadrant, so that means we're going north of the line and we're going east of it. But then we have to figure out what the measurement is. So if you look at this, that is actually being measured to the east-west line right now. So that's not what we want. We want the measurement of that same angle from the north-south line, which is up here. So we need to know what this angle is right there. So how do we find it? We just do 90 minus 20 in order to get a nice 70 degrees as our measurement. So it's an important concept there that we can only go to the north-south line. So that's north 70 degrees east. So what about O to B? So O to B is, it looks like it's going in the northwest quadrant of things. And so we have to decide what the angle is going to be. So if you look at this right here, this angle of 40 degrees is actually being measured from the north-south line. If that's the case, then right away we can say, okay, we know that itself is going to be the measurement that we're looking for. So we're at north 40 degrees west. It's kind of weird. Students struggle with it sometimes because they're so used to doing reference angles, but you can get used to it pretty fast. So what about O to C? Well, O to C down here, we have in the southwest quadrant our measurement. So then we have to look over here and say, well, which angle? Is it 75 degrees? Well, if you look at that closely, that's actually being measured to the east-west line. We want what this angle is here, so we have to do 90 minus 75 to get south 15 degrees west as our measurement. And finally, in the last quadrant, if we're going from O to D, we're looking at the southeast quadrant of things, and we clearly see that the 25 is actually the number being measured to the north-south line whenever doing our problems. Okay, the absolute most difficult thing to figure out with bearing problems is basically drawing the diagram. Most students figure out the measurements fine, but then when you're drawing a diagram, how do you do that so that it's accurate? Well, just remember, anytime you change a direction, always, always, always draw a north-south line. That will always help you when doing these problems, and I'll show you how that works. It says a boat leaves the entrance to a harbor and travels 25 miles on a bearing of north 42 east. Okay, so right away we're starting at, let's say, we'll call this the harbor, right? So we always want to draw a north-south line, and if you want, you can draw a nice little east-west as well, but the north-south line is what's important wherever you start. So if we're going north 42 degrees east, that means we're clearly going in this direction, northeast, right? And it says that we're going 25 miles. The thing is what is the actual, we need to fill in the angle or the bearing for this. So they're saying northeast, so we're obviously in the northeast quadrant over here. So, but we're going 42 degrees. So the question is it going to be this angle or is it going to be this angle? Well, you just learned just now that we only measure to the north-south line. So north-south line, right? So that means in this standpoint, this is clearly not it. We are, measure this again, we are using this as the measurement for 42 degrees. So this is an example of a boat traveling 25 miles and at a bearing of north 42 degrees east. Okay, now the next part, it says the captain then turns the boat 90 degrees clockwise. Okay, so let's say at this point, he decides to turn the boat 90 degrees clockwise. Therefore, again, we want to add a north-south line. If you want to put a little east-west in there action, you can as well. But that is a very key component to this. So if we turn 90 degrees, we of course have a right angle right here. And it says we're going to go 18 miles. All right. So we'll just do sort of an estimate of what that's going to be. So if we actually then complete this, it says it says 18 miles and a bearing of south 48 degrees east. So this is where it gets tricky. So we have to change our perspective. So we're no longer looking at from the perspective of this north-south line. We're now looking at the perspective of this one. So of this north-south line, we're actually southeast is in this quadrant over here, down and to the right. And if we're going 48 degrees in that direction, we're coming from this line, right, to the north-south line. So that means this angle right here is going to be 48 degrees. That angle right there. So what you basically have a setup here, and I'm sure you know where this is going just by what the picture looks like. But if you look at the first question, it says, how far is the boat from the harbor entrance? Well, last time when we left the boat, it was about right here, and the harbor is here. So that means if we connect this, what they're looking for is this side. Well, clearly we have a right triangle, right? So therefore, we can look at this and go, well, we have two sides right now. So that should be pretty simple to figure out. Let's say that x is the missing side. So x squared with the Pythagorean theorem would be 18 squared plus 25 squared. We would get a sum of 949. So when we take the square root of this side, we're going to get positive and negative 30.8 miles. Obviously, you can't have a negative miles, number of miles, so the result in our problem is 30.8 miles. Okay, if we look at the picture, this number makes logical sense because if this is indeed a right triangle, as we know, that would be the longest side of the triangle with 18 and 25. Okay, the last question is a little bit trickier. So it's asked, what is the bearing of the boat from the harbor entrance? Okay, so remember, right now we know that this is where the boat is, right? We know that this is the harbor entrance, right? We'll say H for harbor entrance. So we want to know the bearing from the harbor entrance, okay? So the bearing is essentially going to be this angle right here, this entire angle. So why is that? Well, you got to basically eliminate the triangle itself. So if I was to just quickly redraw this, so if I had my north-south line right here, and then I made the little northeast line, and this is the harbor right here, and this is the boat. If we redraw this line, and we wanted to know what the bearing is from the harbor to the boat, then we have to measure the angle to the north-south line. So that turns out to be this big line right here, blue. We already know the part of it is 42, so that means we have to figure out what this angle theta is going to be. So if we can figure that out, we can just add to 42 and we can get the bearing. If you look at the triangle, though, we should easily be able to do that because we have a triangle with 18 and 25 opposite the important values. So I'm going to redraw the triangle over here, right here. Right, we got theta here, we got 25, and we got 18. So this is the opposite, and it looks like this is the adjacent, so that's tangent. So we know the tangent of that angle theta is 18 over 25. So once again, remembering to be in degrees, we're going to be doing the tangent inverse of 18 over 25. It's going to be approximately 35.8 degrees. And if you want to know the full bearing, we'll say bearing angle, then that's going to be equal to the 35.8 degrees plus the 42 degrees that was already there, which is 77.8. Just remember, though, this is a bearing, which means we have to have it in that standpoint for the problem. So if you look at the bearing right there, we're in the northeast quadrant again. So we're basically at north 77.8 degrees east, okay, in our problem.